So we were discussing the effect of capacitances in our in the amplifier stages, and one question came up at the end of the last class was the fact that, I mean, we initially were doing integrator, then we did this all this DC analysis using cascode. It doesn't seem like that we need an integrator, right? The point she made up, she came up with, and which the way we approached it, it seems like that is true. So what I thought today is to first take you, I mean, it's a slight digression from the flow that we have been in the path that we are under. But this, since the question came up, it will be a useful digression. So what I'd like to do is to show you under what condition, when this integrator, if you don't consider it to be integrator, things can go down. Okay, so let's start with this, our good old R1, R2 feedback network. And this by now you know is a DFAM. So under what condition your V0 over Vi will be equal to R2 by R1? V0 over Vi is actually what? If I don't assume infinite gain and all, ideally it should be minus R2 by R1 if this is virtual ground. Correct. So this is V0 over Vi, rather H infinity is minus R2 by R1. So under what condition is H infinity valid?
GM is very large.
GM is very large, but in this particular case, essentially GM times R1 has to be infinity, right? So let's go with that thing of GM being very large. Now you can only have, I mean, even from the, if you have started the project, you will see that it's not particularly easy to get very large GMs arbitrarily, right? So you end up burning a lot of current. If you end up burning a lot of current, then your output impedance also goes down. Those things starts to come into picture. So you probably don't want to do that. So what is the other way of increasing GM? I mean, now let me consider only this part. So let's assume that you have optimized your DFAM to death, right? You don't want to go any further with the DFAM, and you have maximized the GM, whatever be the value, but you still need effective higher GM. What I can do is then say that, okay, so your DFAM had a GDS also, and your DFAM had a capacitance also. You have capacitance at various places. Let me only consider the output capacitance to make this point. And this output capacitance is basically summation of the capacitance attached to the output, right? So CDB and all those capacitances attached to the output. So this is C0, let's say. So one way to increase the DC gain, or one way to increase the gain of this op-amp, of this DFAM, is to say that I'll put another gain stage here, right? Let me put a gain stage here. So this was the VE, right? This was the VE, the error voltage. So now if I replace that entire contraption with this, then this will become my VE. And if I put this inside a box, and then I can put a negative feedback around it, right? So this essentially is the agenda. Okay, so if I am able to do this, what is the effective GM that I am getting?
It will be multiplied by A.
Right, it will be multiplied by. So what is GM? GM is the short circuit current gain with respect to input change, right? So if I short this output and apply a delta, I mean, incremental, let's say VE here, then the output will be A times GM times VE, which means the effective GM has gone up by a factor of A. Okay, so we should be able to do it. But now, I mean, what is A? How do you realize A is not an ideal PCVS? So the best, I mean, till now, whatever we have done, we have been, the best we could do is this. That's why we have been using that, right? If we had anything better, we would have used that. So it essentially means that I have to, instead of A, I have to use that thing here again. Okay, so if I put that thing back, so if A is also our defam, then this defam also has a GDS C0. And let's assume both are identical, right? So okay, so this entire stuff is my new GM, right? I mean, this is not the GM per se, but this is what we expect it to work like a new GM. Okay. Yes.
Sir, initially you have considered the VCVS. Then you have.
I don't have a VCVS. That is a wishful thinking. That was a wishful thinking. We don't have a VCVS, right? We want to make a VCVS essentially, right? So, for example, this architecture here works somewhat like a VCVS because its output impedance is 0, right? Or very low. But in isolation, your GM is not a VCVS.
Right.
But now I want to make a increased GM, right? This A can be a factor of 100, 1,000 or whatever. I mean, if A is 100, I can increase the GM by 100. So since I don't have anything, so I am using whatever I have. Okay. So this is what we wish. If you already had it, then why bother, right? I can use that instead of the pulse GM itself.
Sir, my doubt was like, this is basically a OTA, right?
Correct.
Voltage control current source.
Correct.
But what I am thinking is that the next stage is also a OTA.
Yeah.
So its input impedance is infinite.
Right.
So because there is no loading effect, so it itself work as a voltage control voltage source. That way can we think?
I didn't understand. You mean this? There is no loading here.
So
this is a, yeah, in fact, that is true. What you are saying, what he's essentially saying is that my second OTA is not giving me, it's not pulling any current ideally. So it seems like my GM, but I mean, the output I'll get is like a VCVS. That is true, but the issue is here. I mean, the next issue obviously is the gain at that node is not frequency independent, right? So here, when I say A, I assume it's a frequency independent constant A, right? So we'll see what is the effect of that. So that essentially leads to the discussion. So now, before I go into the discussion, now tell me, I have this R1, R2. Okay, so where should I? So I have this. Or rather, let me write it in that form itself. We have been, whatever we have been writing. A minus 1. Let it be R1, R2. That would be R1, R2. Okay, so now tell me this V0, at which node at the input will go? Will it go to the plus terminal of the first OTA or the minus terminal? Or rather this node. So these two are connected, right? So this node goes to the terminal A or terminal B. And this also goes here, right? It will go to A, right? Because if it goes to it is only when it goes to A, you go around the loop and you see there is a negative feedback, right? Okay, fine. So let me remove this stuff and only concentrate on what we have right now. So now, so if this is the case, what is my and let's assume that your R2, R1 is, for the timing, let's assume that this is your, if you plan to use this as a unity gain buffer, if you plan to use it as a unity gain buffer, then the relationship between V0 over Vi, rather V0 over Vi is your loop gain, right? Because ultimately what you will do, if you want to use it as a unity gain buffer, you will connect it here, you will apply a voltage here. This will be your Vi, right? So, and when you do loop gain, you desensitize your VI, break the loop, and apply a test voltage. In that case, you will desensitize VI, you will break the loop, and you will apply a test voltage. And the relationship between V0 over V test, or rather your L of S, will be V0 over V test. Okay. So now what will be V0 over V test here? Your V0 over V test will be, so for the purpose of a bit more generality, let me call this one GM1, let me call this GM2, GDS1, C01, GDS2, C02. So what will it be? If I express it in the form of some DC gain by 1 plus S by P1, 1 plus S by P2, what will A naught be?
GM1, GM2 divided by GDS1 plus S C01.
No, DC gain A naught will essentially be your A naught is when you're at DC, which means all capacitors are open. So it's effectively individual gains of multiplication of individual gains of GM1 and GM2, right? So that becomes GM1 by GDS1 times GM2 by GDS2 divided by 1 plus S by P1 times 1 plus S by P2. So what is P1? How will you get P1? Let's assume the P1 is associated with this node. So what is P is essentially time constant associated with a node for a first order system, but it seems like these are two isolated first order system coupled together. So what is P1? So what is the time constant associated with that node, highlighted node?
RDS1 times C01.
Yeah, so which means that the pole associated with the 1 over the time constant, that is GDS1 by C01. So 1 plus S by GDS1 by C01 times 1 plus S by. Okay.
Is this C01 is the overall capacitance from two stages, right? The output of the first and the input of the second
Yeah.
stage.
So essentially, whatever capacitance you see at V0 under the feedback condition is clubbed into C0. Right. So ultimately, I mean, it boils down to breaking the loop again. So ultimately, your loop will be something like this, which means that there is an input capacitance here also. So the C02 will, the input capacitance of GM1 also gets clubbed into the output capacitance of GM2. And that is why you get, I mean, in this particular configuration, you get this. Okay. So, yes.
For GM1 transponder to the output, from the output there will be impedance in that side.
This side?
Yeah, this side.
Okay, yeah. Fine.
So GDS1 is even that is okay. But there will be also impedance in that.
Well, what will be that impedance looking into GM1?
1 by GM.
Why?
Because this is not a voltage source.
Okay, but when you have broken the loop, is there any feedback across that GM? Then how will you get 1 over GM? No. What I think his question, if I understand correctly, is what is the input impedance looking here? Or the output impedance of this GM1? That is infinite, right? Because what is this? I mean, your def amp is a combination of GM, GDS, C01.
Input zeros, output.
Yeah. Yeah. So I mean, find out the output impedance of anything, standard thing, input 0, output. We'll see, figure out, apply a test voltage at the output and see what is that. Okay. Anybody has a confusion about this? So the question boils down to what he's asking is, this is my GM. This is GDS, this is C0. What is the impedance looking here? Is that finite or infinite? That is infinite, right? Because that is the output impedance of the OTA neglecting its GDS. right? So OTI is this entire GM, GDS, C0 put together. Okay, so that does not mean, this does not mean that I can extract the GDS and throw it out. So this is just a model. So when you put an output impedance, when you make an OTA and check the output impedance, you will never get infinite because GDS comes along with it. You will not be in simulation or in actual life, you will not be able to isolate this GDS, but in a model, mathematical model, you can draw anything. So this makes our life easy. So that's why we do it, right? Okay, fine. So now, couple of things. One is we are doing all these things to ensure that we get large GM, or in other words, in this case also, we want this product to be really large, right? We want A0 to be really large. So some assumptions, we want A0 to be, A0 is much, much greater than 1. Okay. So if that is the case, and now let's assume that this is your L of S. And this is your model. Okay. So what will be your V0 over Vi? V0 over Vi is 1 by 1 plus 1 by L. Right? Standard stuff. Okay. So which is equal to what in terms of if I retain those A0, P1 and everything, right? So this becomes 1 plus 1 plus S by P1. Okay. So this becomes fine. So I write it in the standard form of second order equations that we are familiar with, I mean zeta, omega n, and all those things. And let me only call it A0 because A0 plus 1 will be equal to, approximately equal to A0. Okay. So this denominator is now of this form, standard second order control system type form, which is S square plus 2 zeta omega n S plus omega n squared. Right? I assume you are familiar with this zeta and all these notations, right? Okay. So which means your omega n is P1, P2, A0. What is zeta? P1 plus P2 by 2 under root P1, P2. So which is 1 by 2 under root A0. Okay. So now when you see A0 to be really high and P1 to be of the same order as P2, right? Because we have used kind of identical GMs. So P1, we know that we have assumed that A0 to be much, much greater than 1. And let's say P1 is of the same order as P2. May not be exactly same, but similar. Because we have used identical GMs, which means they will have identical properties, which means P1, we can assume that P1 is of the same order as P2. So if this is the case, what is zeta? What is zeta tending to? Zeta is tending to 0, right? So what happens when zeta, or this is zeta is damping factor, right? In a second order system. What happens when zeta tends to 0? You get underdamped, really underdamped kind of expressions, right? So which essentially means that if the open loop transfer function has high gain and two poles close to each other, that it's when you put it to negative feedback, the closed loop transfer function will have very low damping factor, right? So the conclusion from this is if P1 and P1, P2 are close by and DC gain is high, right? A0 is much greater than 1. This is for L of S. L of S is open loop. Then V0 by Vi in closed loop will have underdamped response. And what is essentially meant by underdamped response is the fact that, let's say you have this L of S. Let me put this L of S like this here directly so that it now behaves like whatever you are more familiar with by this stage. So if you give a step input here, the output will ring like crazy and finally settle. Okay, so what is the expected output when initial, I mean, second class or third class, third lecture we had started, what is the expected output? The expected output is probably something like this, neatly settled to the final output, final value. So this is V0 expected. Initially, we were not getting, we'll probably be, I mean, if this is expected under the condition of infinite gain, okay? So if you don't have infinite gain, it will never reach its final output desired value. There will be a steady state error. If we have to reduce this gain, I have to increase the gain. If you have to reduce the steady state error, I have to increase gain. One way to, I mean, we have explored many ways of increasing gain, cascode and all. Let's say that is also not enough. Now we want to put two stages together to increase the gain. Then if you're not careful, you will end up with this. Okay, so let me repeat what I said. So essentially, the conclusion from all of this, assuming it's a two-pole system, very critical, this is assuming it's a two-pole system. If you have two poles very close by and with high DC gain, when you put such a system in negative feedback, you are likely to get severe underdamped response. Okay, make sense? Okay, fine. So essentially the problem, I mean, there are a couple of problems with this. One is how to fix it, definitely. And the other is we seldom have a second order system, right? So this is with only two OTS, two poles. But in reality, you have can have so many poles. In fact, you can have, I mean, you will have as many poles as the number of capacitors. And capacitors can be in numbers, right? So does that mean that, I mean, how should I at least go about analyzing it? Yes. Okay, so that's a good question. So his question is, it seems like here, so I mean, it seems like there is a problem with this high gain, right? If I have high gain, in fact, that is one of the conclusions. Thank you for bringing it up because I should have addressed it. So it seems like it's possible. I mean, it seems like it's, if A0 goes to infinity, whatever be the location of P1, P2, this tends to go to 0, right? But that is actually not a correct interpretation. I was planning to come to it as a later stage, but this thing, since you have brought it up, let me address it, right? So your zeta is 1 by 2, 1 by underscore A0. So let's assume that P1 and P2 are not close by. Okay, so let's assume P2 is much than P1. Okay. So then what does this expression reduce to? Zeta becomes 1 by 2, 1 by under root A0, under root P2 over P1. Okay. So this is under root effectively P2 over 4 A0 P1. So now you see, you kind of get a handle, right? So what is the condition of underdamped? What is that thing? Zeta should be less than or more than 1, right? If zeta, if you want no, I mean, critical damping case is the fact that when zeta equal to 1, so your output settles without any ringing. So if zeta has to become 1, then all I have to ensure is that the second pole P2 follows, I mean, the ratio of P1 and P2 is 4 times the DC gain. Right? So essentially means that if the DC gain is high, you have to ensure that the second pole is even higher away, farther away. Right? So that's essentially the conclusion, assuming it's a second order system, second order all pole system. I haven't even considered zeros. Okay. So it was a good question that it seemed like that having high DC gain is detrimental for stability. By stability, I mean it doesn't settle cleanly, it rings. But it's not the case, because if you assume that the poles are not bunched together, they are separated, it is possible to still stabilize it under certain condition for a certain DC gain. And the condition is this. And if you keep on increasing, I mean, if P2 is even further away, then your zeta is more than 1, which means it's going towards more and more overdamped case. And the extreme case is if P2 is at infinite, which means it doesn't even exist, then it becomes a first order system. You have a single pole system, and in that case, you get all the single pole settling things, right? Yes.
The location of pole, as you say, that you need to adjust, but it's dependent upon the capacitance.
Yeah. So that is a parasitic capacitance that comes with the devices.
But we don't have to adjust.
You have separate capacitance to put.
Additionally, we have to.
Yes. So how would you so now that you know this, right? Now that you know this, yes. Okay, I mean, let me redraw, then we'll talk about it. Right? So. Okay, now let me, I mean, what was your question? Okay, so yeah, so you're saying that, I mean, we are taking the output from here. Fine, so? No, we are not assuming. Okay, so why I said that if we assume this, it is possible to stabilize. But I mean, this is mathematically true for P1 also, right? You can do either. It really doesn't matter. Okay. I mean, as far as the stabilizing maths is concerned, it really doesn't matter. I mean, it's symmetric with respect to P1 and P2, this expression. So you can as well make P1 to be much greater than P2. Okay. So that's not a problem. But let's assume that you have decided to make P2 much greater than P1, or rather P1 now is much less than P2. So what will you do? Let me remind you, your P1 is 1 by, or rather P1 is GDS1 C01, and P2 is GDS2 by C02. So what will you do? And these are close by because you have used identical stuff, and not so now what is your strategy? The intrinsic capacitance cannot be changed, but you have in your IC, in your PDK, you have extra capacitances. You can add capacitances if you want. It's difficult to remove capacitances, but it's always easy to add capacitance. Yeah, right. So essentially, you have to, if you cannot make P2 to be very large with respect to P1, you can always make P1 much lesser than P2, right? It's relative dreading kind of thing. Okay. Don't try to do that. So I can say that I will put extra capacitance here. Right. So let's say, let me call it C extra. So this, now your C extra plus C01 has to be what? C01 has to be if I just look at this expression, it should be P2 by 4 N0, right? It should be P2 by, that's right? P2 by 4 N0. Okay. So what is P2? This is GDS2 by C02 by 4 GM1 GM2 by GDS1 GDS2. Something is wrong. So this is GDS2 by C02 times 1 over 4. Yeah, what we are saying?
The extra plus C1 equals to GDS1 by P1. P1 is P2 by this P1. It should be GDS1 equal to by 4.
Okay. I understand what you're saying. Yeah, that makes sense. Okay, so essentially what we want is now the new P1 is essentially your GDS1 by CO1 plus C extra. This should be equal to P2 by 4 N0. Okay. So I mean, if we assume that C extra is much greater than C01, because that anyway we have to do, because that's we are shifting the poles, which effectively means that your C extra will be 4 A0 GDS1 by P. Okay. So
One question.
Yes.
The location of P1 and P2 depends on A0 or not?
we'll see. Okay. So once you put everything together, you will find, right? So location of P1 and P2.
Suppose this C extra is not there.
Okay.
Just this circle is there. So
Then it depends, right?
it will depend on the A0.
Yeah, because okay, so if you don't put C extra, then it's only what is A0? A0 is GM1, GM2 by GDS1, GDS2. And your C0, I mean, your poles are also GDS1 by C01, GDS2 by C. So that they definitely depend. But if you have to make them independent, then you have to take away something, right? So how do you control poles? You can control poles by adding capacitance. So we are saying that you can put an extra capacitance at a certain node, and then I'll make it independent of the DC gain. Okay, so that's the whole idea of it. So this essentially gives you the handle of figuring out what will be that C extra B. Because what is A0? A0, how did you come up with? A0 you didn't just pluck out of thin air, right? A0 is determined by a top level specification. Let's say I told you want a top level gain of this much, a DC gain of that much. That fixes your A0. Okay. Once your A0 is fixed and you want certain type of response in terms of settling, which essentially means that your P2 is also kind of fixed, because it's the relationship between P0 and P1 and P2 that will determine how good your settling is, whether it's underdamped, overdamped, critically damped, and so on. Okay, so I will come to this more formally, but this is what I wanted to, because the question was raised last class, why should we at all bother about this integrator stuff? The reason we should bother about this integrator stuff is because of this. Now, if C extra is much higher than GDS1, then I can assume that this is kind of an integrator, right? So this effectively becomes GDS1 by, at reasonable frequencies, this becomes the expression of this, the rate at which this node reacts with respect to VE is VE times GM1 by SC extra, ignoring GDS1, right? And now I'm okay with this because this, since C extra is much, much larger with respect to anything that you have in the circuit, the effect of this C2 will come much later. So what I am trying to get at here is, now I think it will be slightly more clear. So without this putting this C extra, our Bode plot would have looked like say not, let's say you have P1 here, let's say you had P2 somewhere here. So it would have looked like this. Okay. But now you have now you have changed P1. Have you increased P1 or decreased P1 by putting C extra? You have decreased P1. So your P1 is gone down from here to somewhere here. But your DC gain hasn't changed. So your response will now become something like, so this was 20 dB per decade. This was 40 dB per decade. So this will go something like this and then go by 40 dB per decade. Okay. So now when you have a response like this, how would you express this part of the curve?
Integrated.
Yeah, this is integrator, and more mathematically, your total expression of A naught, a total expression of L of S was A naught by this. Okay, so let me call this P new, P1N. Okay, so between, this is P1N. So for omega less than P1N, how do you express L of S? Bode approximation? A naught. So for omega greater than P1N less than P2, that is this region of the plot, how will you express L of S? Bode approximation. So you can neglect this term because S is less than P2, omega is much less than P2, that is the Bode approximation. So this becomes A naught by 1 plus, or rather you can neglect 1 also, S P1N. Okay, so what is this? So this is an ideal integrator. Okay, so you have an integrator like response in this part of the frequency response. Then after this, when omega is greater than P2, your L of S becomes A naught by S square P1 P2 P1N P2. Right? So now your integrator like response is lost here. Okay, so one of the reasons why we want to do an integrator like, get an integrator like response is because if you have an integrator like response around the unity gain frequency of the loop, your output, settles like a first order system, right? So again, I haven't proved this rigorously, but if you go back to the previous lecture, we assume that if you have a first order system, omega u loop is essentially the rate is essentially 1 over time constant of the closed loop system. So your integrator like response around omega u loop is essential to ensure a proper settling of the output. Okay, so again, I mean, this is not a rigorous proof, so let me just make the statement. The statement is integrator like response around omega u loop will make the system behave like a first order system. Okay, so intuitively this should make sense because ultimately your first, ultimately, when does your feedback exist? Your feedback exists around as long as your gain is high. And if the gain is high, you want it to behave like an integrator, as long as the gain is high. So your gain is high below omega u loop. So you want it to behave like an integrator below omega u loop. So that is the intuitive reasoning. But again, this is not a mathematically proved reasoning. I'm making that intuitive reasoning that if you can ensure that you're around the omega u loop, you can ensure that it behaves like an integrator. Your loop gain behaves like an integrator. The output response will behave like a first order system.
Closed loop output.
Closed loop output response, obviously, right? So essentially, if you have something like this, let's say you have P1N here, and you have omega u loop here, and you have P2 here. This, to a very crude approximation, can behave like a first order system with a time constant of 1 over omega u loop. And it will not have ringing and all those things. That's the hypothesis, right? So I am trying to convince you that this can, intuitively this makes sense. Does it intuitively make sense before I go ahead and try to be a bit rigorous about this? So what did we, let me quickly recap. So what did we start off with? Firstly, we wanted to see, we want to get a good GM. There was only so much amount of GM we could get using whatever methods we can think of. Then we thought that we'll put maybe another gain stage before that GM to enhance the GM, to increase the DC gain. The issue becomes when you put two of these stages together and close the feedback loop, then you can get potential ringing. Ringing, I mean, you have underdamped response, right? It goes up and down and all those things. So when that happens, it's a problem. And that is happening because the closed loop poles are very close by under the condition of when the gain is also very high. The closed loop poles being very high, closed loop poles being close by under the condition of gain being very high, essentially means that you will have minus 40 dB per decade roll off around omega u loop, right? So this was the original omega u loop. So this is not an integrator-like response around omega u loop, right? When you didn't have the C extra, it wouldn't, around omega u loop, it wouldn't have looked like a integrator-like response. So then we also proved using our underdamped equations that this is a condition which is not, this is a condition which will lead to zeta to be much less than 1, around 0. So you will have a lot of ringing. So since you do not want that, we figured out that we probably have to separate the poles. I don't want to compromise on A0, but I still want stable system. So I thought I'll separate the poles. So we separated the poles. P2 we kept where it was, and we lowered P1. Since we lowered P1, it is probably now possible, if we lower the P1 sufficiently at lower frequency, it is possible to still get an integrator-like response. This plot doesn't really show that, but this plot kind of shows that if you lower P1 sufficiently, it is still possible to get an integrator-like response around omega u loop. Now, note that your omega u loop might have changed, right? So initially, your omega u loop probably would have been something here, somewhere here. Okay, this is still not, doesn't look like 40 dB per decade. So maybe your omega u loop would have been here, but just because you want to stabilize the system, you wanted to push P1 at lower frequency, you ended up getting a smaller omega u loop, but still your system will still be, your system can still be stable, right? If you have to choose between a fast system and an unstable system, you would rather choose if you have to choose between an unstable system and a slower system, you would rather choose a stable system which is slower, right? And then a very fast system which is unstable. So there are many good things about negative feedback. one very bad thing about negative feedback is it tends to make your system slower. Because if you are trying to make very fast systems using negative feedback, which essentially means that all the poles are very high frequencies, which essentially means that all the poles are probably even bunched together. If all the poles are bunched together, then you put in negative feedback, you will have underdamped response. So in essence, in order to make your system look like, make your system stable, you'll have to separate the poles. I have made all these arguments with two-pole system, but these arguments can also be made using multi-pole systems also. But take my word for it at the moment that as long as you can separate the poles far apart, and you can make the system look like a first order system around the UGB of the loop, around omega U loop, you should be fine as far as the stability of the system is concerned. But this now comes at the cost of the bandwidth of the system, because your omega U loop has to go down, right? You can say that I can move P2 away. I mean, I can also, I said that I will move P1 at lower frequencies, but I mean, if I have a circuit technique that pushes P2 away, then probably I can get away without reducing omega U loop also, right? I keep P1 wherever it was. If I could push P2 away, then maybe I would have ended up with something like this. Then omega U loop would have been here, much better. But it's always difficult to move poles to higher frequencies, right? To some extent, it can be done. We'll see one example where it can be done, but not always it's possible to move poles to higher frequencies. Okay. Okay, so good point. What he is saying is that if you put two capacitances in series, it's likely to move poles away, right? Because C1, C2 parallel is lesser than either C1 or C2. But the issue is one of the issues is you don't have access to this terminal of C2. It's a parasitic capacitance intrinsic to the device. If I had access to the terminal, I would have even opened it, right? No capacitance then. Since you don't have access to the terminal, you cannot do that. Yes.
So by looking at the Bode plot, we can decide whether the system is fast or slow just by looking at the omega U loop, right?
Yeah.
If it is high, then its system is fast.
Yeah.
Small.
Right. Okay.
And sir, how the location of P1 is getting changed by C extra? Is there any...
Yeah. So what is C extra doing? This is your P1, right?
So sir, if the C extra is high,
yeah,
the location of P1 is close to 0, right?
Right.
So, but sir, the higher value of C extra make the system sluggish, right?
Yeah. That's what you are seeing also, right? If you put this extra capacitance, it's pushing P1 lower and thereby pushing your omega U loop at lower frequency also.
And it is also pushing P2 also in a lower frequency.
It's not pushing P2 anywhere, right? P2 is still this.
So P2 is from this expression.
So what is P2 in terms of the transistor parameters? P2 is this. So this is for a given P2. How do you fix P1? Right. Okay. So let me. So now one question. The question that I would like to ask you is that will this system is underdamped, but if you wait long enough, your output will settle, right? But is there a condition under which the output will never settle? It will keep on oscillating. Zeta is equal to 0, right? So when essentially zeta becomes exactly equal to 0, that is when A0 is infinity, you have this problem. Okay. So we don't have A0 to be infinity, but we want A0 to be pretty high. So this can still likely be a problem. Now, let me take you through one more situation.
Sir,
yes.
So if A0 is infinity, in that case, the location of P1 and P2 will be?
Tell me. So A0 becoming infinity means you want A0 to be very high, right? P2 is still wherever it was, right? Now, if you don't do anything with P1, if you leave it as is, then you have a problem. Isn't it?
So can you just go to the expression of P1? Okay, so if A0 is infinity, then P1 it will come to the 0, right? So that's why it will...
Yeah, so that should behave like an ideal integrator then, right? If C1 is C extra is also infinity, then you have infinite gain, but after that it starts to drop.
But sir, will there be ringing or for a step, if I give a step response, in that case, will there be any ringing or it will be like a ramp?
So if you can maintain this relation, there won't be any ringing, right? So this essentially says that A0 times P1 has to be some P2. Okay, so if you can maintain this relation, there is no ringing. If you cannot, and if P2 becomes lower than this, then you will have ringing. Okay. So now, I mean, okay, so one might say that, hey, I can get by without too much of gain. Okay, I can get by too much of gain, maybe infinity we anyway cannot shoot for. So is this a problem? So this is now, as it turns out, if you want larger and larger gain, you will probably have more of these blocks cascaded together. And even if you don't have more of these blocks cascaded together, you have internal capacitances which we have kind of conveniently hand waved off. So essentially means that the system can be of higher order. Okay, so let's assume such a system which has L of S to be A0 by 1 plus P1 whole cube. Okay, so I simply took all the poles to be in one location because it's easy to do the maths, but it's not necessary. Right? So third order equation, it becomes messy. So just to make a point, let's assume that all the poles are at single location. So now what I will try to do is to try to convince you the fact that before I try to convince you, tell me one thing. So your V0 over Vi is L by 1 plus L. Okay. So if Ls by 1 plus Ls, if Ls at some frequency, at some S, so let's say S0 is equal to -1, what do you conclude about such a system? At some omega naught, I should say, not S. Some omega naught is equal to -1. So this, which means V0 over Vi is infinite at some omega naught, which means this is kind of an oscillator. It's an unstable system. Okay. Pardon? Okay, so not necessarily. So we'll get to that. But if I just stare at this equation, it seems like we have to steer clear of this condition of Ls equal to -1 at any frequencies. So if we hit this loop, if for some omega naught, if L of S is equal to -1, we are in trouble. This is the only conclusion that you can get out of this expression. And this expression is called Barkhausen criteria if you have taken control system courses. So now, so let's figure out whether this condition can occur if in a third order system. Okay. So by the way, in a second order system, this condition occurs when zeta goes to 0, right? Can occur when zeta goes to 0. Where was that expression? When zeta goes to 0, you have S squared plus omega n squared, right? So, so this becomes an oscillator in a closed loop sense, right? Okay. So now let's see what happens. Under what condition I can get V0 over Vi to be infinite. Okay. So which essentially means that I'm looking for a omega where 1 plus L of j omega naught goes to 0, right? So 1 plus L of j omega naught, or rather I mean it's easier to express in this form, 1 by L of S, because all the S terms goes to the numerator then. So I'm looking for a condition where 1. So this is finding roots of L of j omega naught. Okay. So if I, or rather 1 plus L of j omega naught. So if I replace S by j omega naught, what do I get? So this becomes A naught plus 1 plus j omega naught by q equal to 0. Ah, right. Thank you. Okay, so now, I mean, we do the standard stuff. We have to ensure that both the imaginary and the real part goes to 0, which means that I club this A naught plus 1 minus. I hope you are looking into the algebra. I am doing it on the fly. There can be mistakes. Plus J omega naught by P1. Make sense? Okay, so I set, so this is the imaginary term and this is the real term. If I set the imaginary term to be 0, I get omega squared by P square, P1 squared to be equal to 3. Right? And I put that here. So your A naught plus 1 minus 3 times 3 equal to 0, which means A naught is equal to 8. So at a modest gain of 8 in a third order system where all the poles are bunched together, you are satisfying that Barkhausen criteria. Okay, so you become greedy and you wanted to put 3 systems together and you see that you can at max get a gain of 8 before your system becomes unstable. Okay, so which means that, I mean, as the saying goes, more is not always better unless you know how to use it. Right? So this is a classic example of that. You put multiple stages together, put it in feedback. It's likely that the system will become unstable. Now, note that one might argue that I have made the algebra simpler by assuming all the p's to be bunched together, but it need not necessarily be the case. They can be slightly away from each other, but essentially whatever is happening is still valid. Okay, so if you look at the Bode plot, what does this system look like? This system essentially looks like you have all these p's poles bunched together, which means this goes by minus 60 dB per decade. Right? So if I wanted to, but I mean, again, by the statement that I made earlier, you would want your system to behave like a integrator around omega u loop. So this is your new omega u loop, where it crosses the 0 dB line. But clearly it's not an integrator. You have minus 60 dB per decade roll off. So if you could change only one thing, what we would change? If you had 3 poles here, right? You take one of the poles and move to lower frequency. So you move this pole, maybe I should have more space. You take one of these poles, move it to lower frequencies so that it goes by 20 dB per decade. And then you hit 2 other poles and it goes like this maybe. Okay, so not here per se, so the pole was somewhere. Okay, so this is one way of, potentially one way of stabilizing. Again, this is a very hand-wavy way I have dealt with it. This is strictly not rigorous. I will try to be a bit more rigorous in the next class, but again, I mean, this is a whole branch of control systems, right? So if you want to understand it from that point of view, I would encourage you to go back and look into all the stability criterions that our control system friends have come up with, right? Ruth Hurwitz, root locus, Nyquist, Bode, blah, blah, blah. So all of them are there because of some reason, it's useful. So we will look at it in a slightly more, I mean, and next class, we have 2 more classes. Basically, in the next class, I will look at it in slightly more detail, which will give you a bit more intuition, because I can understand today's class can be a bit confusing. Simply because, I mean, the stability criteria came out of nowhere. It seemed like things were all good till last class. Suddenly things are not stable. Right? So it might take some settling time in your mind. So take that settling time. We'll discuss it in the next class in a bit more of detail.
Sir?
Yeah.
One question.